Chapter 18, Part 1. I'm about a day behind on getting these up online, but we just finished the second exam, and I hope the histograms, which I find quite interesting, and also kind of the way that all of us determine grades for a course. I hope that is somewhat illuminating if you want to have an office hour or show up at office hours and ask, like, what the hell does that mean? Feel free. Okay. Chapter 18 deals with alpha-Reactivity. So does 19. And I'm going to touch on both chapters today. So alpha-Reactivity is what makes carbonyl chemistry really interesting. So you know that nucleophiles will add to the carbonyl. And that can be a reversible reaction if it's hydride or a carbon nucleophile. That's not a reversible reaction. But nucleophiles are often quite basic. For example, you know Grignard reagents will add to the carbonyl, but as you figured out or learned or maybe was surprised, the fact that these can also be strong bases. So if you have a base, if your nucleophile is basic, you can also, and I apologize, I guess, I'm going to throw competing reaction arrows here and just say that carbonyls can be turned into enols or enolates. Of course, whatever your nucleophile was, nucleophile slash base was, that's where the proton ends up. And if it's something like ethoxide, then these are turned into being reversible. Sometimes enolate formation is generally reversible, but sometimes it's almost irreversible if your base is very strong. Now, these are competing reactions, and maybe one of the beauties or difficulties of organic chemistry is that nucleophilicity and basicity frequently parallel each other. And so there's other factors like steric hindrance that mediate this reactivity. And we can talk about solvent and stuff like that. Okay, so if you're going to talk about basicity and removing protons, we need to talk a little bit about pKa. I thought I'm always using a pencil, and I don't think I've ever pointed this out. This is in case you're interested, this is a black, I'm not sure, how do I turn this? There you go. A Blackwing 602, and I really love these pencils. They're not super cheap. Buy them online. Particularly like this, half the pressure, twice the speed. So they're pretty, they've got a long history behind them. Okay, so basicity. Acetone, as I've mentioned in the past, has a pKa of about 20. And aldehydes more acidic, although they are so reactive you might have trouble finding a pKa value. I'm talking about this proton. Not the aldehyde proton. That is not acidic, right? The orbital that's involved with this carbon-hydrogen bond is perpendicular to the p orbitals, which we're looking down on here, a bird's eye view. And so there's no interaction with those, of those two sets of orbitals. I told you that esters are more stable than ketones and aldehydes because of their resonance stabilization. So what that means is they start lower down in energy, and so if you want to deprotonate them, it's more difficult, or this is less acidic. So the pKa of ethyl acetate is about 25. Okay. Now, think about that in terms of ethanol and the use of something like sodium ethoxide. The pKa here, of course, as you know, is about, well, your book in the next chapter talks about 16. I'm going to say that methanol is 16, and I like to think of ethanol as 17, and isopropanol and T-butanol get up closer to 18. Okay, so these are thermodynamic properties, and that's in contrast. We always contrast thermodynamics and kinetics, and I'll talk more about that later and how that plays out. Now, what that means, the fact that these protons can be removed and you can make things like enolates, meaning you can use the enolates as nucleophiles. All right, so and perhaps I am sorry. Let me start that over. If you have acetaldehyde and you put that in the presence of sodium hydroxide, you will do a base catalyzed deprotonation of the alpha position, and you will make an enolate. Similarly, if you take acetaldehyde and put it on under acidic conditions, you have a longer set of reactions, but you will protonate the carbonyl. You always protonate the oxygen of any carbonyl if you're going to protonate anything, and then the proton falls off. Sorry, that's completely wrong. This time I'll use the eraser. Pushing the electrons up to the positive charge. And I'm just going to say minus H plus. Of course, H plus in outer space has an extraordinarily high energy. So we never really actually have H plus. This has to be going somewhere, right? So, you know, whether it's the counterion of sulfuric acid or whatever. So, acidic conditions, you will reversibly form enols, and under basic conditions, depending on the base, you will reversibly form enolates. And the reason that's important is that if you have an enolate, and there's usually, if you think about the pKa's here, there's usually a lot more of your carbonyl than there is of your enolate. And if that's true, then the enolate can act as a nucleophile. I already have that up arrow there. And so you have an electrophile and a nucleophile, all in the same package. And that's true here as well, that you have this enol with this very electron-rich double bond, and that can attack your protonated, activated carbonyl. So here's the basic version, here's the acidic version, and what you get out of that is carbon-carbon bond formation. I'm going to just do, yeah, no, sorry, I guess I already have that arrow there. And keeping everything. So here's the basics reaction scheme. Here's the acidic reaction scheme, and you'll notice there's only negative charges here, there's only positive charges here. Now if you're starting with acetaldehyde, you make a different, this is protonated, but I'm just going to ignore the proton now. This reaction product is called aldol. That is the name of that compound. If I put my thumb over the proton and the positive charge, that is called aldol. The reaction is the aldol reaction, and that's chapter 19. But it's coming, and it's coming up soon. Now, maybe that looks kind of boring. It's actually, gotta admit, carbon-carbon bond formation, and I'll show you how this is actually critical if you want to think about complicated molecules like erythromycin, which is a very, very important antibiotic that most of you have probably taken. The aldol reaction, so is really important, but let me further talk about that. Yeah, the acetaldehyde has no stereochemistry. It's achiral. The product aldol has a stereogenic center. All right, it's got one, right? I'm not showing up or down because it's going to be racemic, because of course we're not controlling stereochemistry here. But what if we had propionaldehyde? Propionaldehyde. All right, one more carbon. Simple, right? We have a carbon here, and we have a carbon here. And now we should imagine I've just drawn the Z isomer of the enol. We will also form the E enol, and when we make the aldol product, talking about aldol as a reaction, not a compound, because this is not, you'll have 1, 2, 3, 4, 5, a hydroxypentanal, but it's actually a methyl hydroxypentanal, 2-methyl, 3-hydroxypentanal, but we have not only one stereogenic center, we actually have 2 now. So 2 diastereomers. Oops. Are what we will form. Right? So there's a lot going on here. And there's a lot to talk about and think about. And so let's get really started on this. And I guess that'll be part 2.